So let's look at entropy in a statistical way, right? We have 5 coins that we're flipping. And what are the odds of all the possible outcomes of that coin flip? And what do I mean by that? Well, what are the odds of getting 5 heads in a row? What are the odds of getting 4 heads and 1 tail? 3 heads and 2 tails? 2 heads and 3 tails, 1 head, 4 tails, or 5 tails, right? Those are all the possible outcomes of flipping 5 coins. You can have anywhere from 5 heads to 5 tails or anywhere in between. These are called macro states. Because normally when we look at 4 heads and 1 tail, we don't care which coin was the tail. We just want to know that one of them was tails. But the macro states here, it looks like there are 6 possible outcomes, so each outcome should be just as likely, right? But that's not true at all. If we look at the micro states, if we look at each possible combination by treating each coin as an individual entity and looking what is the outcome of coin number 1 flipping, coin number 2 flipping, coin number 3 flipping, and so on, we see that there are far more than 6 possibilities, right? So the possibility of 5 heads, there's only one possibility, right? Every coin has to be heads. So there's one possible microstate where each coin is a head. What about 4 heads and 1 tail? Well, that's actually a little more complicated because there are 5 possible outcomes, right? The 5th coin could be tails, or the 4th coin could be tails, or the 3rd coin could be tails, or the 2nd coin could be tails, or maybe the 1st coin is tails. All 5 of these possibilities will give you the outcome of 4 heads and a tail. But there are 5 possible combinations that give you that outcome, whereas 5 heads, there's only one combination. Let's look at a little more detail. What about 3 heads and 2 tails? Well, maybe the last 2 coins are tails, or maybe 3 and 5 are tails, 2 and 5, 1 and 5, 3 and 4, 2 and 4, 1 and 4, 2 and 3, 1 and 3, or 1 and 2. These are all the possible combinations of having 3 heads and 2 tails. 2, 4, 6, 8, 10 possible outcomes, double what we just had before. The possibility of getting 2 heads and 3 tails, I actually didn't write that down. It's identical to this one, except replace each H with a T and replace each T with an H. The possibility of getting 1 head and 4 tails is the same as this, except again, replace the H's and T's. The possibility of getting 5 tails is the same as getting 5 heads, except replace the H's with T's. So, looking at all the possible states, right? There's one microstate for that macro state. Here there are 5. Here there are 10. Here there are 10. Here there are 5. There's 1. So you are far more likely when you flip 5 coins to get some combination of heads and tails, 3 heads, 2 tails, or 2 heads and 3 tails, than you are to get all heads or all tails, right? So what are the total number of outcomes? For the macro states, it looks like there are only 6 outcomes, but in reality, there's 16, 26, right, 31, 32 possible outcomes. So the probability of getting 5 heads is 1 in 32. The probability of getting 4 heads and a tail is 5 in 32. The probability of getting 3 heads and 2 tails is 10 in 32, and so on. So you are far more likely to get a disordered system when you roll than an ordered system. Now, this dramatically increases when you add more coins. If we did this with 6 coins, 7 coins, 8 coins, 9 coins, and so on, it becomes much, 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 much less likely that much less likely that you will get an ordered system over a disordered system because there are more disordered systems. So entropy is just an argument that in all things being equal, a system is far more likely to be disordered than ordered. So let's look at a conceptual example. Let's ignore the coin flips here. And let's look at a perfume example. We'll take a room, and we'll have a divider down the middle of that room. And on one end of the room is a complete vacuum. On the other end of the room, we have, say, helium molecules, or helium atoms. We have air, we have helium, bouncing around. Right now, we'll stick with 5 helium atoms. And we'll number them 1, 2, 3, 4, 5. Like we had with coins, 5 coins. Each of these is an independent atom. It'll bounce around on its own. If I remove this divider, actually I'm going to keep it there just as a dotted line. So this we'll call side 1 and this is we'll call side 2. So even though the helium all started on side 1, it's moving so quickly that when I take a snapshot of where the helium is, we can have different outcomes. We can have all 5, so if this is side 1 and this is side 2, we could have all 5 helium in side 1 and none in side 2. We could have 4 helium atoms in side 1, where 1 is over in side 2. We could have 3 in side 1, 2 in side 2, 2, 3, 1, 4, 0, 5. And if you look at the possible combinations, they're identical to the coin flip experiment we just did, right? Because the odds are the same. The odds of flipping a coin, heads or tails, is 50-50. The odds of a helium atom being in one side of the room or the other is 50-50. So for small numbers of helium atoms, 5, it's not completely outrageous that if you took a snapshot at some later time, that all the helium would be back on that side of the room, right? There's a 1 in 32 chance. The 32 possible microstates, one of those microstates is having all the helium on side number 1. That's not outrageous, 1 in 32, right? That's not crazy. But now, with like a perfume, right? Imagine a mole of helium. 6.02, I should say, not 1. 6.02 times 10 to the 23 helium atoms, not 5. So almost a trillion helium atoms. And then they're all start on the same side, side number 1, but you let them go. They move randomly about the room. Each helium atom is independent of the motion of the others in this experiment. You take a snapshot. What are the odds of all the helium being back on that side of the room? Ridiculously small, right? You have to, it's like flipping a coin 6.02 times 10 to the 23 times. That's a 6 with 23 zeros after it. Almost a trillion coin flips and coming up heads every single time. Is it possible that can happen? Yes. It's not impossible. Is it likely for that to happen? Absolutely not. You're more likely to win every Powerball event you enter than for all the atoms in a room to go on one side. So think of the room you're in. It's entirely possible all the atoms could decide to be found on one side of the room, creating a vacuum on the other. We don't worry about that because the odds of that happening are so ridiculously small, we don't worry about it. So this is entropy. It's a state of disorder. We say that this ordered state here, where all the atoms are on one side of the divider, is a higher ordered system. When we remove the divider and the atoms are free to spread about, that is a disordered or a higher entropy system. Is it statistically possible for these atoms to go from the high entropy back to the low entropy system, back to the ordered system? Again, yes, it's statistically possible, but it's not probable. In fact, it's very, 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 very improbable. And that's just with 1 mole of gas. There's more than a mole of gas in the room you're currently sitting in. So entropy is a statistical argument that you can make that it's more likely that these atoms will be displaced. Next semester, if you're in this course for Physics 142, the last experiment we'll be doing a radioactive decay experiment. I'm not allowed to irradiate you, so we'll be doing a dice rolling experiment. I will give you 200 six-sided dice, and you will shake those dice and then remove any ones that come up with a 1. Well, what are the odds of rolling all 6s, getting a super duper Yahtzee, right? 200 dice, the odds are 1/6 raised to the 200th power. That is a very, 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 very small number. Roll 10 to the 1 to roll all 6s. Incredibly unlikely. However, whatever you do roll is also just as unlikely, but you got it. There are just far more of those disordered systems, so they're with a 1/6 of the dice being rolled a 1, a 1/6 of the dice rolling a 2, a 1/6 of the dice rolling a 3, and so on. There are more of those disordered systems than there are ordered systems. And my video is getting choppy, so I'll end it there.